Hey guys, it's Monday. We are starting a new mini unit just this week. We're going to take kind of a different look at chemical reactions where we're going to compare them to physical reactions. We're going to look at properties, tell you about that later. Look at properties of matter of the reactants and the products, and we're going to try to figure out, did a chemical reaction actually happen or is this something else? That's what we're talking about today. So first, I have two examples here where you burn paper and where you rip it. My question is, which of those is a chemical reaction and which is a physical reaction? So give me those two sentences. I'm assuming if you're here, you missed live class. So go ahead, pause me, type in those little pink spaces right there. Which one do you think is the burning? Which one do you think is the ripping? The ripping is a chemical or physical. Is the burning chemical or physical? Go ahead and pause me and we'll keep going. Okay, I'm going to tell you all about our sciences of the day, our learning targets. In breakout rooms, we're going to do a little practice with chemical and physical changes. We're just going to do like the first of, I think we have 8. And so we'll do the first one. I'll actually show you the first one. We'll do the first 3 of 8 together, and then you'll do the rest down here for your independent work. Finally, we'll do your exit ticket. We're actually going to create some rules for how we're supposed to know if something is a physical or a chemical change. That's what we're building towards today. You guys, this week, these few weeks, they've been announcing Nobel Prizes, which is like the top prize in almost every scientific field. That's not true. There's medicine, which is kind of like biology. There's chemistry and physics and economics and literature and peace, which is the weirdest one. And I might be forgetting one because I thought there was 7. Yell at me if you can figure out which one I forgot. So this is Dr. Emmanuelle Charpentier, that's her, and Dr. Jennifer Doudna. They're French and American chemists, and they won the Nobel Prize today. And they won it for this amazing technology that you might have heard of. It's called CRISPR. If you know about CRISPR, Google or watch a YouTube video. And so in YouTube, write, what is CRISPR? And watch somebody explain it to you because it's super cool. Basically, it's like this fancy chemical way for editing DNA. So do you want a dog that has 2 short feet and a puffy tail and curly ears? Well, that maybe isn't easily done yet, but soon it will be with this CRISPR. You can basically take genes that you want, stick them together to make all the genes that you want, which is basically like this new tool that can be used in so many different ways that we don't even know all the ways it can be used yet. And so it's just like it opens the door to everything. The other big deal is that before these 2 won, in the last 120 years, only 5 other women won this prize. They give the prize out every year. Usually they split it between people because people work together. Very rarely is, in TV, there's always like one scientist in a lab discovering things by himself. That almost never happens. That's kind of crazy. Usually scientists partner with each other. I do this, you do this, and then you say something that makes me think something, and I write a thing, and that makes everybody's ideas kind of get swirled up together, which actually makes it hard to choose who should get a prize sometimes. This graph, let me get my face out the way here. This graph actually talks about this. It only goes up to 2014, but it shows you, they're right here. Which one did I miss? Oh, no, there's only 6. I got them all, you guys. Here's chemistry. This is the Nobel Prize that they won. Before 2014, only 4 women won it. So since 2014, there's been one other woman won it in 2018. And then these 2 women won it this year. So now there's 7. But look at how many men have won it, 165. Jeez Louise. So that just shows you a couple of things. How, because of how culture works and the culture of academia and stuff, women tend to get kicked out. Not kicked out, but subtly pushed away from hard sciences. Maybe it's like, no, you may not have this job as a professor at my university, which is like a really hard no. And sometimes it's more like, oh, well, you're a woman, so let me talk to you about becoming a nurse or a teacher, which are great things to be, but I want you to have all of the options ahead of you. So I wanted to highlight that these two women won chemistry Nobel Prizes, and you could too if that's what you want to do. So just in general, we need to push and pull women and people from all backgrounds, of all languages, and from all countries into STEM, into science, technology, engineering, and math, just so we can have more perspectives. There will be more about that. Look at this physiology medicine, and this doesn't include all of them either, because last week or a few days ago, three more white men won for their medicine. So they did not make good scientists of the day. They're not great role models for us, but we're probably over 200, definitely over 200 since 6 years ago. Okay, so today we're creating rules. That's the end. At the very end, we will create rules to differentiate between physical and chemical changes. Remember that to differentiate means to tell two things apart. I can differentiate between my left and right shoe by looking at their patterns and going, oh, this one like this one's like this. All of you were bad at that at one point. I know, because my 3-year-old is always like, is this on the right foot? And I go, no. And he goes, okay. And he doesn't care, and he runs around with the shoes on the wrong foot. But whatever. He's learning to differentiate between those two things still, to tell them apart. So here are our definitions. And you think that I'm just giving it all away, but it's actually harder than it sounds. So a chemical change is any change that makes new substances with different molecules. That means the atoms rearrange to make new molecules. This is not a new idea. We talked about this last week. A physical change is something that changes, but it's only the size or the shape or maybe the state of the substance, but not its molecules. The molecules are still the same molecules, just something else changes. So here's an example. Burning a candle is a chemical change. When you burn something, you are taking oxygen and in this case, it's the wax, and you're burning it, and you're heating it up, and the oxygen and the wax, which is just carbon and hydrogen, react, and they release a smoke, and it changes new molecules. Physical change would be like breaking glass. This is like the time when I was 5 years old, and my neighbor kid was I lived in California at the time, but for some reason he was throwing rocks over my house, and I was like, okay, I can throw rocks over my house. That's cool. I'm 5, and he's like your age probably, right? So he's 12, and he's throwing rocks. You guys can pick up a rock and throw it over a tiny house. So I tried to do the same thing. Guess what? It didn't go over the house. It went straight through my bedroom window, which is exactly like what you see in this breaking glass picture. But that is a chemical change, because that's still glass. It did not create a new molecule. It just broke it. It changed its shape or its size, you could say. So that breaking glass would be an example of a physical change. You guys know this, but just as a quick reminder, the reactants come before the arrow, the substances before a change. The products are everything after a chemical change, or we can just say after a change in this case. So we're talking about not necessarily a chemical. We're trying to decide if it's chemical or physical change. So after an arrow is the products, before the arrow are the reactants. So we can talk about them before and after. We don't have to say like the before things, the after things. No, we can say reactants and products. Okay, so we will learn more about these properties of matter, but I want to introduce them to you real quick. A property of matter is a trait. It's a characteristic. It's something about the matter that is true for it. So that could be its odor. Odor means smell. When it stink, does it stink? Does it smell like sugar? Does it smell like smoke? What does it smell like? That's odor. That's this odor word. Taste. You are actually a very highly sophisticated chemical detecting machine. You have chemical detectors on your tongue. You call them taste buds. You call them taste buds. Your taste buds are fancy chemical receptors, and you can taste things that are sweet. Those are sugar molecules. And you taste things that are sour. Those are acids. And you taste things that are maybe not great for you, and those are usually bitter. Foods that are bitter or tend to be like that. Anyway, smell, and you have them in your nose too. That's why smelling and tasting, you are sensing molecules. You're sensing chemicals, which is very cool. So different matter could have different shapes, could have different textures. It could feel rough or smooth. Definitely could have different colors. Flammability is its ability to flame, to burn. This is its burnability, but we don't call it that. We call it flammability. Can it burn easily or not at all? Boiling and melting points are the temperature at which something boils. For water, it's 100 degrees Celsius or 212 degrees Fahrenheit. But luckily, your aluminum pan that you're boiling your water in, its melting point is way higher. So it will not melt at that temperature. You have to heat it up really hot, thousands of degrees, before it'll melt. Density is how packed together something is. We'll talk more about density tomorrow, I think. Yeah. So here's why this is important. Because during a chemical reaction, and guys, this is like the thing for this week. So listen up to this blue thing right here. During a chemical reaction, atoms rearrange, making new molecules. You know that. If that happens, if you make new molecules, you should see different properties before and after the reaction. So we're trying to figure out, how are you going to know that a chemical reaction happened? Well, the matter should change. You should see that the color is different, and it smells different, it tastes different, and it was smooth and now it's rough. It used to be able to burn, but now it won't burn. If you change the properties, it means that you've changed the molecules, which means it was a chemical reaction. Okay, so here's just a quick example. This rubber ball is round. It smells like rubber. It's solid. It's bouncy. It maybe is like rough. If rubber tends to be kind of rough to the touch. These are just different properties of a rubber ball. Okay. So let me close out of this. So this is the one that I'm going to do with you before I send you to breakout rooms. This is what you're doing today, basically. Remember up here that a chemical change, the atoms rearrange to form new molecules. Physical change, that didn't happen. They're the same molecules as before. So here's your example. Ice is melting and turning into water. Your reactant is ice, your product is water. So what are the properties of ice? Let's see, ice is a solid. It is clear, kind of, translucent would be a better word, but I'll call it clear. I was like color. It tastes like water, honestly. When you put it in your mouth, it tastes like water. It melts into water. These are things that we know about it. Okay, water, it is liquid. It's also clear, unless it's dirty. It tastes like water. I don't really know how else to call it. And it can freeze into ice. Okay, so some of these things are different. Its state is different. But we know that H2O is the molecule of water, and it stays H2O when it's ice. And it easily moves back and forth. I can freeze ice in my freezer, take it out and melt it, and then freeze it again and melt it, and it goes back and forth easily. This is actually a physical change. Physical change. This is what I want you to do for each one. And some of these are going to be much harder. And I actually prepared what I wanted to say for this. So you guys take more time than I just took. Think about what are the properties of the before and the after. This is the big one for me. Taste. Remember, like I said a minute ago, your tongue is really good at sensing chemicals. You can sense chemicals with your taste buds. And so if the taste is changing, that is a really good indicator. It's good evidence that a chemical reaction happened, because now your tongue can see that there are new substances, new molecules being made. The fact that they're both clear, it's also like, oh, they're both clear, okay. But the taste the taste staying the same is good evidence that these molecules are the same. It's still water molecules. All that happened is that they slowed down over here, right? When they're ice, they're just moving really slow. You want to speed them up, give them a little energy, increase their average kinetic energy, and they turn into water. Okay, so in your breakout rooms, You guys are doing the first 3 of these 8. So let me just do, I'll skip this one, boiling water. Guess what? It's a lot like melting water. It's also a physical change because, I don't know why I'm whispering, but because it's essentially the same. You have water, it's still water. It's just now steam. It's water gas. It's water vapor, but it's still water. You can turn it back into liquid easily. It's not, the color isn't the same and the taste isn't the same, but you might see here that just giving it more energy doesn't change the molecules. What about number 2? What about fireworks exploding? You might see down here that I'm giving you little hints. So let's think about the odor. Anybody smell fireworks before? I don't know. It might just smell like paper and gunpowder or something. I don't know. Gunpowder. That's kind of what's in it. It's like a black powder inside of paper, and it can burn. It's flammable. And I now know that these should be much bigger so you guys can see. Okay, so over here, the properties. When you explode a bunch of fireworks, you guys know it because you can smell a lot of smoke. Why is this not coming up? Smell. Okay, here we go. Sounds like smoke. Makes bright light. Where'd that light come from? Its color afterwards, it maybe is like burnt color. I don't know. It depends, like ash. It's not flammable anymore. After you burn something, it doesn't burn again. And so all of these things, it's changing its flammability. Its smell changes. Remember, smell is another thing that you're good at detecting chemical reactions, chemical changes. So this is definitely a chemical change. Okay, so I want you guys to do more of these. Here's mixing baking soda and vinegar. Think about the taste, the odor, the state. If you can, go home and do this. Don't put very much. Put a tiny bit of baking soda and vinegar. You won't get in trouble, but you can see the reaction. It's very cool. Chopping a log. You have a log and you hit it with an axe and you break it into 2. Is that a physical or chemical change? What if you burn that log? What are the properties before or after? Think about the color, the smell, the flammability. What about when you make Kool-Aid? Or anything else? We like to eat Crystal Light. It's got like the fake sweetener in it, no sugar, but still. But you take it and you put it in water. You're basically just dissolving sugar in water, and you like spin it around. Think about the color of this powder, the color of the liquid. Think about what it tastes like. What does the powder taste like? What does the liquid taste like? Think about what it smells like. Is it a physical or chemical change? What about a rusting car? You leave a car out in the rain for a long time and it rusts. Think about the color. Think about the texture. Physical or chemical change. What about when you cook something? You fry an egg. What is it? Color. Oh, I wrote color and texture still. What is it? What about the taste? It would be a huge one. The smell, the color, the texture. Tell me about before and after and determine if it's a physical or chemical change. Okay, last slide, your exit ticket. There's no quiz. What you need to do is go back up and look at those. Do you see some trends? Can you use those to create rules for what is a chemical change, what is a physical change? So we know there's a chemical change if this is happening, or this is possible, or these types of changes are chemical changes. What about a physical change? So there's certain types that are always physical changes, and certain types are always chemical changes, etc. Give me some rules, please. That's it. Then turn these in, and your teacher can take a look at them, and we'll talk about them tomorrow in class. Thank you, guys.